So week 3 takes you through deriving rasters. You've done some of that in Price. In one of the early chapters, you created a hillshade, um, and you talked about different capabilities. And then if you were in 246, we did that in a mini lab, and we also did that probably as part of your tsunami exploration. So anyway, when you derive rasters, basically they're talking about creating a raster from another raster, and we'll be working primarily with digital elevation models. So the first raster that they talk about is a slope raster. So you can get slope in two different formats. One, you can get the degree of slope. The other is the percent of slope. These are the formulas. Rise over run times 100 gives you your percent slope. And the degree slope is basically using geometry to figure out the angle and the tangents. And luckily, you don't need to know the formula. You just need to know which is which and which is used for which. One is preferred for engineering, and I think percent slope is more transportation, and the degree slope is more scientific research. So when we look at slope, we're looking at the difference in elevation between each cell and its neighboring cells. And so this is looking at kind of the topography or the land elevation changes. And so you use that when you want to know speed of flow, you want to know how fast a river can flow, erosion rates. Oh, I have that right. And that other thing is right there. And so there is a slope classification that automatically spits out your slope. And you can change that. And if you lose it, you can use the remove the graphic option in your properties and choose and find the slope values again. The aspect uses slope to figure out slope and elevation to figure out which way something is facing. So is it a northern aspect, western aspect, and it uses that 0 to 360 degrees. I wonder actually, because the distance rasters, the direction rasters don't use 0, I wonder if it actually does use 0. I'll have to take another look at that, or you can take another look at that. But anyway, it's kind of looking at which way that slope is going to face. And so when we look at slope, or this is aspect, isn't it? We're going to change that. Yeah, when we look at aspect, flat values have, so I'm wondering if actually 360 is not on here because it would overlap with 0. So I don't know how they look at that. Anyway, that said, flat areas have, if there's no slope, it's a value of -1. So 0 would be due north, 180 would be due south, and when it's divided kind of in these kind of categories, I think normally when you run a slope, you get these 8 1, 2, 3, 4, 5. Yeah, you get 8 pi sections or 8 categories, and they're generalized this way. But you get to change them to be anything you want. You could break these down in a lot of ways. So then there's a bunch of questions about, how you would use slope. A lot of solar energy, solar panels use slope and aspect. Gardening, facing houses, buildings, all that kind of stuff. You kind of want to know which side is something facing. One of the concepts they talk about in this lab is the quality of the raster. And so if you have a very high resolution, you will get a high resolution output. So, and what they're talking about is the size of your grid cell. So if you have 100 meter by 100 meter grid cell, that's pretty huge, and that would maybe be good for, state level or continental level. I've seen some global climate grids that are 1,000 meters by 1,000 meters. So that would be a really low resolution raster. Elevation rasters with cells like 30 meters by 30 meters are pretty good if you're looking at a whole state. You can get that generalized shape and feel and information, but if you want to zoom in on a city or a town or a small area, you really want to look at, oh, 10 meter, but even lower than that if you can. So you get that kind of blocky, choppy horizontal resolution, and that kind of gives you an idea that that was probably not the best DEM for the use that you chose to use it for. So here's an example of creating a flow path based on a 30-meter resolution DEM and a 10-meter resolution DEM. And you can see that the 10-meter resolution DEM gives you a much finer grid or a much finer line in developing that raster, deriving that raster. The other aspect of a DEM that you can or may not be able to see is the vertical resolution. So the horizontal resolution tells you how big that pixel is. The vertical resolution on a DEM should tell you what are my elevation values, right? So, and sometimes you can't find that information. If you don't have the metadata, if they haven't included that in the metadata, you may need to put some other known value and compare your cells to see what that value or that resolution is. So if you have big jumps in your resolution, if you move from, let's say, 10 feet in elevation to 100 feet in elevation, even if your grid cells are very small, you still have a pretty poor vertical resolution. But if you move from 2 feet to 4 feet to 6 feet, that has a much higher vertical resolution. I misspoke a minute ago. One of the things they'll ask you to do is to figure out the horizontal units and the vertical units, and that's what I was trying to talk about with using another file. And that may have been in an earlier lab actually. But the horizontal units are usually the linear units in the metadata about the DEM. So when you look in the properties, you should be able to find the horizontal units. So whether it's feet, meters, miles, whatever, that would be your horizontal units. But you may not know when you look at a DEM and it spits out a bunch of numbers that give you elevation. You don't know if it's feet, meters, inches, centimeters, or whatever. And if that's not recorded in your metadata, you really don't know how to check that. So lots of ways to do that. And actually, I'll leave that up to you to figure that one out. Okay. So the lab asks you to figure out a bunch of quantifying techniques. Do you want to find the slope, the elevation, the aspect? So obviously, if you're trying to find which peak would be better to have in a challenge, you want the elevation. Alaska wants to do cross country. They need a low slope, but not too low, so they're going to use slope. And this guy wants, what's he looking for? Heights, water. So he needs elevation, and he probably also needs slope on that one. So the second part of the lab, then, so you'll do some derived slope and aspect rasters, and then you're going to do some problem solving with those, picking some good sites based on those features. So let's actually, before we move on, let's see if I have those up. Quantifying, no, I think it was, yeah, hold on a sec. So with the quantifying lab, you start out with aspect and slope, and you run some raster calculator values that say I just want slope from that meets some criteria. And when you run that raster calculator, you get a yes/no configuration. So I think I ran it a bunch of times to play with it. But so here is my yes/no raster calculator. So the green grids met whatever criterion I set up in my statement, and the purple do not meet my criteria. So if I were to make this hollow, And this is, and so see, here's where I got into trouble just doing this without thinking about it. I don't know whether this is was my slope or my aspect. I just kind of kept letting the raster calculator do its thing. And so that's really poor GIS work. So when I do that in slope, I'm going to assume, well, I don't know. Let's take a look at here. Ooh, no, I think this was a slope criterion. I wanted low slopes. And so I could check that by making that hollow and say, yeah, it really did work. This is giving me almost all the low slopes. And then, so my guess here is that this next one is my aspect. So there's my aspect, and we don't know. And I'm gonna, the ones are kind of the yes values. So let's see what my aspect. Oh yeah, so there's my aspect. So that met my aspect criterion. So one of the things that I've got now is this really nice yes/no file that I can do some raster math. So if I were to add my raster calculator together, which I actually could do because that would be really fun to see what happens. So I'm going to turn on my I'm going to turn on something here. Yeah, I'm getting really slowed down website. But anyway, so I could try this. They have a plus tool that would let me just add them together, and I could search for the plus tool, which would probably be the safe thing to demonstrate for you, but okay, so I'm going to go into spatial analysis. There's map algebra. What if I just added those two together without the plus tool? Let's just see what would happen, just because I'm only at 12 minutes. This is taking a long time to pull up, but let's let it go here. Okay, so I'm going to say raster calc 7 plus raster calc 6. Again, what a really dumb way to name those things. It gives me no information, but I'm pretty sure this is good slope and good aspect, which I've never liked aspect. Okay, so I'm going to go ahead and set that. It's in the right geodatabase. I've named it something somewhat reasonable, and I'm going to OK it, and let's see what I get. Yeah, I'm getting total nothing on that. It's total slowdown. I don't know what's going on, unless I did you guys see if I did something weird? Oh, things are very cool. So what I get is a 0, a 1, and a 2 value. And what I know is if I add 0 and 0, I'm going to have 0. So this means none of the criterion were met. A 1 means at least one of the criterion was met, either the aspect or the slope. A 2 means both of the criterion were met. So now I have a raster that I can open up the attribute table if the thing will actually work today. La la la. I can select those 3 now. There we go. That value number 3. Nope. Here we go. Where did I do? I'll open up. Yeah. The value number 2. Sorry. I can use the conversion tool and convert those to polygons. So I have a specific now polygon feature that includes both my aspect and my slope. So it's a pretty cool little tool. Okay, so in the other parts of this lab, you're going to look at hillshades and contour lines and view sheds. It's pretty easy to do that. I always keep the defaults. I don't understand enough about that to change that. If I were living in a different part of the country, maybe there's some standard altitude and azimuth that they use to get good illumination. And then one of the things I know is that when I want to symbolize my hillshade, you always put your DEM in the layers above your hillshade, and the DEM is the layer that has a transparency, and it's the layer that is colored. Your hillshade is left in black and white. Okay, contour lines are lines of equal elevation. You will need to specify the interval. So it depends on how much you're going to be zoomed in and how many lines you want on your map. You can set a base contour, and remember that's not the minimum, it just is the beginning calculation value. And then the last piece of this is you create a view shed, which is kind of a yes-no raster as well. I think, yeah, so when I created my view shed, I have areas that can be seen from the lake and areas that cannot be seen from the lake. And now that I have this 0, 1, I could export those ones as a polygon, and then I could do some geoprocessing with my good land, slope and elevation, and my view shed, and find only those areas that meet that specific calculation. I wouldn't have to rely just on visualization for that.